Welcome, and let the world grow soft and quiet around you. As your breathing slows, all on its own, imagine turning your face toward the summer sky, low toward the south, where the pale river of the Milky Way runs thickest and brightest through the dark. Somewhere behind that glowing haze, far beyond the crowded stars and the long veils of dust, lies the still and silent heart of our galaxy. And at its very center, a black hole holding the weight of 4 million suns. Its name is Sagittarius A-star, and it has been turning there, patient and quiet, since long before the Earth was made. Tonight we will drift toward it together, one gentle fact at a time. There is nothing at all you need to hold on to now. Just breathe and let go, and welcome back to Beyond the Stars. The first fact is that Sagittarius A-star is a black hole, not a distant curiosity in some other galaxy, but the great dark heart of our own, the single object around which the whole slow wheel of the Milky Way quietly turns. There is no other object of its kind anywhere within 1 million light-years of here. It is what astronomers call a supermassive black hole, a name they give only to the very largest ones, and it holds within itself the weight of some 4 million suns, gathered into a space smaller than the orbit of Mercury. It has no surface, no shore, no light of its own, and yet it is there, real and steady, at the center of everything we call home, turning quietly in the dark tonight, as it always has. The second fact is that Sagittarius A-star sits at the exact center of the Milky Way, the still point of our enormous spinning galaxy. Every one of the hundreds of billions of stars in this galaxy, our own sun among them, is drifting in a slow, patient circle around that one place. The galaxy is a great slow wheel, and this is the small dark peg it turns upon. If you could rise far above the flat disk of the Milky Way and look down upon it, you would see the great luminous pinwheel of it, all its arms curving outward, and there at the very middle, hidden in a blaze of crowded stars, the small dark point that anchors it all, the quiet hub of the wheel we ride upon. The third fact is that when you look toward Sagittarius A-star from the Earth, you are looking toward the constellation of Sagittarius, the Archer, low in the southern sky of the northern summer. Many people know that patch of sky by a simpler shape, a little pattern of stars that looks remarkably like a teapot, complete with handle and spout. In the old star charts, the Archer's drawn bow points almost exactly toward the galactic heart. And here is the loveliest part of it. For the steam that seems to rise from the spout of that teapot is in truth the glowing haze of the galactic center itself. Aim your eye just there, a hand's width off the spout, and you are looking straight toward the heart of the galaxy. The fourth fact is that the distance from you to Sagittarius A-star is about 26,000 light-years, which means the light and the radio whispers reaching our telescopes tonight set out on their journey when the last great ice age still lay heavy across the northern world, when mammoths walked and no city yet existed anywhere on Earth. Every image we have of it is that old. We are not watching the galactic center as it is now, but as it was, a message posted long ago and only now arriving. And in all that unimaginable span of time and space, it has simply been turning, quietly, patiently, entirely unhurried. The fifth fact is that a black hole, at its simplest, is a place where gravity has become so strong that nothing at all can escape it, not even light itself. Gather enough matter into a small enough space, and the pull it makes upon the surrounding fabric of space grows steeper and steeper, until at last there is a boundary past which every possible path leads inward. Past that boundary, gravity has simply run out of directions that lead back outward again. Beyond that line, light cannot climb back out into the sky, and so no picture of the inside can ever reach us. It is not a hole in any ordinary sense, not an emptiness, but a place where gravity has quietly closed over itself. The sixth fact is that Sagittarius A-star belongs to the class astronomers call supermassive, which is a plain and honest word for a black hole holding somewhere between 100,000 and many billions of times the mass of our Sun. These are utterly unlike the small black holes left behind when a heavy star collapses, which weigh only a few suns and are scattered by the thousands through the galaxy. Between the small black holes and the supermassive ones lies a puzzling gap astronomers are still working to fill. The supermassive ones sit alone at the very centers of galaxies, and they are somehow bound up with how galaxies form and grow. Ours is one of the smaller and gentler of that great family, modest as monsters go. The seventh fact is that you can never see Sagittarius A-star with your eyes, and not only because it is a black hole. Between us and the galactic center lie some 26,000 light-years of the Milky Way's crowded disk, and strewn through that distance are vast, cold clouds of gas and fine grains of dust, drifting in long dark lanes. Those long dark lanes are plainly visible to the naked eye as rifts in the summer Milky Way. Ordinary visible light simply cannot pass through them. The dust absorbs and scatters it away until almost nothing survives the crossing. And so the very heart of our own galaxy is hidden from our sight behind a curtain of dust, near and yet utterly veiled. The eighth fact is that the veiling is far more complete than you might guess. For astronomers reckon that visible light from the galactic center is dimmed by something like a factor of 1 trillion before it reaches us. Out of 1 trillion photons that set out from that direction in ordinary light, perhaps one arrives. If that dust were somehow lifted away, the crowded core of our galaxy would blaze in our night sky as a great glowing ball, brighter than any star, casting shadows on the ground. But the dust is there, and it is patient and thick. And so instead we have a soft, quiet, indistinct glow low in the summer south. The ninth fact is that our own Milky Way is what astronomers call a barred spiral galaxy. A broad, flat disk of stars with graceful arms curling outward and a straight bar of stars laid across the middle. The whole disk is perhaps 100,000 light-years across, thin as a sheet of paper compared to its width, and swollen at the center into a bulge of older, redder stars. The bar of stars funnels gas slowly inward, feeding the whole central region across enormous spans of time. Sagittarius A-star lies at the innermost point of that bulge, the very hinge of the bar. Everything else, every arm and cloud and star, wheels slowly about it, in a rotation that takes hundreds of millions of years. The 10th fact is that we live very far out in the suburbs of this galaxy, on a modest little spur of stars that astronomers call the Orion Arm. Our Sun and its planets drift there, roughly halfway between the crowded center and the thinning edge of the disk, in a quiet and unremarkable neighborhood. Living far out from all the action has almost certainly been very good for life on this planet. It is, in truth, a rather peaceful place to be. Out here the stars are widely spaced, the radiation is mild, and nothing much disturbs the long, slow turning of the worlds. The great drama of the galactic center is very far away, and we watch it gently from a safe and distant porch. The 11th fact is that the region around Sagittarius A-star is the most crowded place in the whole galaxy. A dense swarm of stars packed together far more tightly than anywhere near us. In our own neighborhood, the nearest star to the Sun lies more than 4 light-years away, across a gulf of almost perfect emptiness. Close encounters between stars are common enough there to reshape their orbits over just a few million years. But near the galactic center, stars are packed millions of times more densely, so close that if you lived on a world in that place, your night sky would blaze with thousands of stars brighter than Venus. A sky so full of light that true darkness would never quite arrive. The 12th fact is that, despite the name, Sagittarius A-star is not a star at all, and never was one, The name is simply an inheritance from the way radio astronomers label the bright sources they find in the sky. They mark the strongest radio source in a constellation with the letter A, the next with B, and so on down the alphabet. So the brightest radio glow in Sagittarius became, quite plainly, Sagittarius A. Within that broad radio region sits one small, intensely compact point, and that point is what we now call Sagittarius A-star, a name born of bookkeeping and grown into legend. The 13th fact is that Sagittarius A-star is remarkably quiet for a supermassive black hole, and that quietness is one of the kindest facts about it. In many other galaxies, the central black hole feeds furiously on infalling gas and blazes as a quasar, outshining every star in its galaxy combined, hurling jets of matter for thousands of light-years. Astronomers describe such a black hole as quiescent, which is a gentle and remarkably accurate word for it. Ours does nothing of the kind. It sips only the faintest trickle of gas, and glows very dimly indeed. We live beside a sleeping giant, one that has settled into a long and gentle quiet and shows no sign of stirring. The 14th fact is that nearly every large galaxy we have ever examined turns out to hold a supermassive black hole at its center, which is one of the strangest and most beautiful discoveries of modern astronomy. Andromeda has one, far heavier than ours. That tight relationship between a black hole and the bulge around it is one of astronomy's most striking regularities. The great elliptical galaxies hold monsters of billions of solar masses. Small galaxies hold smaller ones, and the weight of each black hole is closely tied to the weight of the bulge of stars around it, as though galaxy and black hole grew up together, shaping one another. A partnership written into the structure of the universe itself. The 15th fact is that Sagittarius A-star is by far the closest supermassive black hole to the Earth, and that nearness has made it the most carefully studied one in all the sky. The next nearest is in the Andromeda galaxy, more than 2 million light-years away, 100 times farther. Almost everything we now believe about black holes was tested first, and most carefully on this one. That is why so much of what we understand about these objects comes from ours. It is our laboratory, our teacher, the one example close enough to watch in fine detail. We are, in a quiet way, fortunate to live in a galaxy whose dark heart is near enough to know. The 16th fact is that on a clear, dark summer night, far from any town, you can look toward the galactic center with nothing but your own eyes. The band of the Milky Way widens and brightens there, swelling into a great soft cloud of light where it passes through Sagittarius, and the dark dust lanes cut through it like slow rivers. What you are seeing is the massed glow of countless millions of stars in the inner galaxy, blurred together by distance. The black hole itself is invisible, but you are looking straight at the great luminous cloud that surrounds it. The 17th fact is that the broad radio region called Sagittarius A is really a whole complex of things, and it took astronomers many patient years to sort them apart. There is a great shell of glowing gas, the remnant of an ancient exploded star, which they named Sagittarius A-east. Sorting one crowded radio region into its separate pieces took astronomers the better part of 2 decades. There is a graceful 3-armed spiral of warm gas streaming inward, called Sagittarius A-west. And buried at the very center of that little spiral is the compact, unwavering point of Sagittarius A-star, the still heart within the swirl, no bigger to our instruments than a single unresolved dot. The 18th fact is that our sun, carrying the Earth and all the planets with it, is falling endlessly around Sagittarius A-star at something like 230 kilometers every second. That is a staggering speed, far faster than any rocket we have ever built, and yet the circle is so vast that we notice nothing whatever. Nothing you can feel or measure in ordinary life betrays that enormous and perfectly silent motion. You are moving that fast right now, as you lie still in the dark. The whole solar system is sweeping in a long, smooth, unhurried arc around the galactic center. And it has been doing so without a sound for 4.5 billion years. The 19th fact is that one full journey of our sun around the center of the galaxy takes something near 230 million years, a span astronomers sometimes call a galactic year. The last time the sun was in the position it occupies now, the very first dinosaurs were only beginning to walk the Earth, and the continents were still gathered into a single great landmass. Astronomers sometimes use the galactic year as a unit when speaking of the deep past of the Earth. In all the 4.5 billion years of the solar system's life, it has completed only about 20 of these circles, 20 slow, patient laps around the quiet, dark heart of the Milky Way. The 20th fact is that there is something quietly reassuring in the thought that our whole galaxy, with all its billions of suns and worlds, turns so calmly around a single silent point that no one has ever seen. The Milky Way does not roar. It does not hurry. It simply wheels, age upon age, in perfect and unbroken patience, and we ride along with it without ever feeling the motion. As you settle deeper into the dark tonight, you might picture that great slow turning going on above you, entirely undisturbed by anything at all. A galaxy revolving gently while you rest. The 21st fact is that Sagittarius A-star was discovered in February of 1974 by two astronomers named Bruce Ballack and Robert Brown, working with a radio interferometer in Green Bank, in the quiet hills of West Virginia. They were not looking for a black hole. Green Bank sits inside a protected radio quiet zone where even ordinary mobile telephones are forbidden. They were simply mapping the radio glow of the galactic center in finer detail than anyone had managed before, and there, amid the broad haze, they found a small, bright, unwavering point that would not spread out no matter how sharply they looked. It was intensely compact and very strange. That single stubborn dot on their charts was the first sight anyone ever had of the heart of our galaxy, found not with a lens, but with a listening ear. The 22nd fact is that radio waves are the reason we found it at all, because radio light passes straight through the dust that blocks our eyes. A grain of interstellar dust is roughly the size of a wavelength of visible light, which is why it scatters and swallows that light so effectively. This one simple property of radio light opened up the entire hidden interior of our galaxy. But radio waves are enormously longer, measured in centimeters and meters rather than fractions of a micron, and they sweep past those tiny grains as an ocean swell passes a pebble, scarcely noticing them at all. And so the dust that hides the galactic center from our eyes is, to a radio telescope, almost perfectly transparent. A curtain that simply is not there. The 23rd fact is that the little star symbol in the name was added in 1982 by Robert Brown himself, one of the two men who found the source. He wanted a way to mark out the small compact point from the broad radio region around it, and he chose that symbol because in atomic physics a star beside a symbol means an excited atom, one brimming with extra energy. Small human gestures of that kind often survive far longer than the people who make them intend. He thought the discovery and the object were exciting. So the mark is not an abbreviation and not a technical code. It is a small act of delight, set down in the notation of science, and it has stayed there ever since. The 24th fact is that the name is spoken aloud simply as Sagittarius A-star, and astronomers who work on it often shorten it further in conversation to Sag A-star. It is a mouthful of a name for something so small and so silent. And there is a certain gentle comedy in the fact that the most important object in our galaxy is known by a piece of radio catalog shorthand with a symbol tacked on for enthusiasm. There was never any grand christening, no ceremony, no ancient myth attached. It simply acquired its name the way a stray cat acquires one, casually and then permanently. The 25th fact is that the very first hint of anything at all coming from the galactic center arrived far earlier, in 1932, when a young engineer named Karl Jansky was investigating static on transatlantic telephone circuits. He built a great rotating antenna of brass pipes and wooden supports, mounted on the wheels of an old Model T Ford, and set it turning in a field in New Jersey. He was 26 years old at the time, and he had no training in astronomy whatsoever. Among the crashes of thunderstorms, he found a faint, steady hiss that rose and set with the stars, and that peaked when his antenna pointed towards Sagittarius. He had, without meaning to, heard the center of the galaxy. The 26th fact is that Karl Jansky's accidental discovery is now remembered as the birth of radio astronomy, an entire new way of seeing the universe. Until that moment, every single thing humanity knew about the sky had come to us through visible light, through the narrow window our eyes happened to open upon. Every new wavelength we have since learned to use has revealed something all the earlier ones could not. Jansky's hissing static proved there was a whole other universe of information pouring down upon us unseen. The unit astronomers used to measure the faintness of radio sources is named the Jansky in his honor. He never returned to astronomy himself, but every radio dish on Earth is, in a sense, his. The 27th fact is that for years almost no one followed up on what Jansky had found, save for one remarkable amateur named Grote Reber, who built a 31-foot dish out of wood and sheet metal in his mother's backyard in Illinois. Working alone at night after his day job, he mapped the radio sky patiently over several years and confirmed that the brightest glow really did lie toward Sagittarius. His careful maps were published in the late 1930s and were, for years afterward, very largely ignored. For nearly a decade he was, essentially, the only radio astronomer in the world. The path that led to Sagittarius A-star began with two curious men, an antenna made of pipes, and a dish in a backyard. The 28th fact is that infrared light became our second great window onto the galactic center, and it is a window that opened only in recent decades. Infrared is longer than visible light but far shorter than radio, and it slips through the interstellar dust far better than our eyes can, though not perfectly. Where visible light is dimmed by a factor of 1 trillion, near-infrared light is dimmed only by a factor of 10 or 20. That difference is everything. It is the difference between an impenetrable wall and a frosted pane of glass. And through that frosted pane, patiently, we learn to look. The 29th fact is that seeing the galactic center in infrared required more than simply choosing the right kind of light, for the Earth's own atmosphere blurs and trembles every image it lets through. Astronomers solved this with a beautiful piece of engineering called adaptive optics, in which a flexible mirror is bent and reshaped hundreds of times each second to cancel out the shimmering of the air above. The mirrors used for this are thin and flexible, reshaped continually by hundreds of tiny mechanical actuators. A laser is often fired into the upper atmosphere to make an artificial star, a reference point for the correction. With that trick, ground telescopes grew sharp enough to pick out individual stars in the most crowded place in the galaxy. The 30th fact is that before adaptive optics matured, astronomers used a patient technique called speckle imaging to freeze the trembling of the air. They would take thousands upon thousands of very short exposures, each so brief that the atmosphere had no time to smear the image, and then combine them carefully by computer to recover the sharpness hidden inside the blur. The method takes its name from the grainy speckled pattern the restless atmosphere paints across every short exposure. Through the 1990s, night after night, teams gathered these frozen fragments of the galactic center and stacked them into pictures no single exposure could have made. It was slow, unglamorous work, and it revealed, for the first time individual stars whirling near the black hole. The 31st fact is that X-ray light gave us yet another way of seeing, and it required leaving the Earth entirely, for our atmosphere absorbs X-rays completely. The Chandra X-ray Observatory, launched in 1999, has stared at the galactic center for millions of seconds of accumulated exposure. Everything above the Earth's air is effectively a different sky, and it took rockets to reach it. It sees the hot gas swirling near the black hole, the flares that brighten and fade, and the faint diffuse glow of the whole inner region. Where radio shows us cool electrons spiraling in magnetic fields, X-rays show us matter heated to millions of degrees. Two entirely different portraits of the very same quiet place. The 32nd fact is that to see something so small at so great a distance, radio astronomers use a technique called very long baseline interferometry, and it is one of the cleverest ideas in all of science. Telescopes scattered across continents observe the same source at the same moment, each recording its data with an atomic clock. Later, the recordings are brought together and combined, and the array behaves as though it were a single dish as wide as the distance between them. Sharpness depends on the width of your telescope. And so, in effect, we built one the size of the world. The 33rd fact is that these radio measurements showed something astonishing about Sagittarius A-star, which is how impossibly small it is. The source of all that radio glow was found to be no larger across than the orbit of the Earth around the Sun, and later measurements shrank the estimate further still. Ruling out every alternative explanation is often harder, and rather more important, than proposing the right one. To pack 4 million solar masses into a space that tight leaves almost nothing it could be except a black hole. No cluster of stars could hold together so densely for long. The evidence arrived quietly in decimal places and error bars, but it was, in the end, overwhelming. The 34th fact is that another elegant clue came from watching how little Sagittarius A-star moves. Everything in the galaxy drifts, and as our sun sweeps along its orbit, nearby objects appear to shift slowly against the distant background. Astronomers call this apparent drift the proper motion, and for this particular source it is essentially nothing. Astronomers tracked the position of Sagittarius A-star for years with exquisite care, and found that its own motion is essentially nothing at all, once our own movement is accounted for. Only something enormously heavy could sit so still while millions of stars stream past it. Its stubborn stillness was itself a measurement of its mass. A giant refusing to be pushed. The 35th fact is that for many years the radio image of Sagittarius A-star was frustratingly blurred, and not by any fault of our instruments. The problem was the turbulent ionized gas lying between us and the galactic center, which bends long radio waves the way rippled glass bends a candle flame. Scattering by the intervening plasma is a nuisance for astronomers studying pulsars all across the galaxy as well. The effect grows worse at longer wavelengths. To see past it, astronomers had to move to millimeter and submillimeter waves, where the scattering finally falls away. That shift to shorter and shorter radio wavelengths was the last technical hurdle, and clearing it made the first true image possible. The 36th fact is that whole observatories were built or adapted for this work, spread across the loneliest and highest places on Earth. The very large array stands on a plain in New Mexico, its dishes riding on railway tracks. The Atacama Large Millimeter Array sits at 16,000 feet on a Chilean desert plateau, where the air is so thin and dry that millimeter waves pass through almost unhindered. There are dishes at the South Pole on Hawaiian volcanoes in the Sierra Nevada. All of them, on certain nights, turn together toward one small point in Sagittarius. The 37th fact is that in the infrared, a marvelous instrument called gravity was built for the Very Large Telescope in Chile, combining the light of 4 separate 8-meter telescopes into a single beam. By blending their light with exquisite precision, it achieves a sharpness no one of them could reach alone, fine enough to track motions within a few light hours of the black hole itself. Combining the light of separate telescopes without losing any of it is an extraordinary feat of engineering. It measures positions to a precision equivalent to picking out a coin on the surface of the moon. With it, astronomers watch things happen very close to the edge, in something very near to real time. The 38th fact is that no single kind of light could ever have told us the whole story, and that is perhaps the deepest lesson of this long search. Radio revealed the compact source. No single instrument is ever enough, and the universe rewards those who look in several ways at once. Infrared revealed the stars orbiting it. X-rays revealed the flares and the hot gas. Millimeter waves revealed the shadow itself. Each window showed a different face of the same silent object, and only by laying them all together did a coherent picture emerge. The universe does not hand us its secrets in one language. It speaks in many, and we had to learn them one at a time. The 39th fact is that the whole effort spanned 90 years, from a young engineer's hissing antenna in a New Jersey field to a photograph of a black hole's shadow, and it involved thousands of people across dozens of countries. Most of them never saw the finish. Long projects of this kind require institutions patient enough to fund a single question for decades. Carl Jansky died long before anyone imagined what he had heard. Many who built the early dishes and wrote the early code are gone. It is a work handed carefully from one generation to the next, each adding a small piece. A quiet, patient relay running across the better part of a century. The 40th fact is that there is something deeply gentle in the thought of all those people, in all those years, working in cold domes and quiet control rooms through countless nights, simply to see one small dark thing more clearly. None of it changed anyone's daily life. No one grew rich from it. They did it because the question was beautiful and because they wanted to know. As you rest here now, you might think of those long nights of patient watching, all of them gathered up into one soft image, and let that quiet, unhurried devotion carry you towards sleep. The 41st fact is that Sagittarius A-star holds a mass of about 4.3 million times the mass of our Sun. That is the single most important number in its whole description, and it is now known with remarkable confidence to within a few percent. That figure has been refined steadily over 30 years of measurement, and it keeps quietly holding up. For million suns, gathered into one point. If you could somehow weigh every star you have ever seen with your naked eye on every clear night of your life, and add them all together, you would still fall enormously short. And yet all of that weight sits in a space you could tuck comfortably inside the orbit of Mercury. A whole crowd of suns, folded into a single quiet dot. The 42nd fact is that we know that mass so precisely because of a very old and very reliable piece of physics, the same one Johannes Kepler worked out 400 years ago for the planets. If you can watch something orbit and you can measure how large its orbit is and how long it takes to complete, then the mass of the thing it circles falls straight out of the arithmetic. The same arithmetic that describes a moon circling a planet describes a star circling a black hole. Astronomers simply applied that ancient rule to stars whirling around the galactic center. No exotic theory was required. The mass of a black hole was measured the same way we measure the sun. The 43rd fact is that the event horizon of Sagittarius A-star, the true boundary of the black hole itself, is roughly 24 million kilometers across. That sounds enormous by any human measure, some 60 times the distance from the Earth to the Moon. Light, the fastest thing there is, would need barely more than a minute to cross from edge to edge. And yet, set against the scale of the galaxy, it is nothing at all, a speck too small to draw on any honest map. 4 million suns are packed inside that sphere, and it would take light only about 80 seconds to cross it from one side to the other. A whole devouring boundary, less than 2 minutes wide. The 44th fact is that the radius of that boundary, measured from the center outward, is about 12.7 million kilometers, and astronomers call it the Schwarzschild radius. It is roughly 17 times the radius of our own sun, which is a gentler way to picture it. Imagine 17 suns laid side by side in a line, and that is the distance from the invisible center of Sagittarius A-star to the edge beyond which nothing returns. The formula for it is startlingly simple, involving only the mass, the speed of light, and the constant of gravity. 3 numbers, and a boundary appears. The 45th fact is that if you were somehow to set Sagittarius A-star down where our sun now sits, its entire event horizon would fit comfortably inside the orbit of Mercury. Mercury circles the sun at about 58 million kilometers, more than twice the width of the black hole's boundary. Everything familiar to us would fit comfortably around it, with a very great deal of room left over. So the whole thing, all 4 million suns of it, would be a dark sphere hanging in the inner solar system with room to spare, and the outer planets would go on orbiting much as before, only very much faster. It is a strange and useful picture. Enormity contained within a familiar circle. The 46th fact is that the event horizon is not a wall, not a shell, not any kind of surface you could touch. It is simply a boundary in space, an invisible mathematical line that marks where the paths of all possible futures bend inward. It is a boundary in the geometry of time quite as much as in the geometry of space. Outside it, you may still turn around and leave if you have engine enough. Inside it, every direction you could possibly travel leads deeper in, and going back out is not merely difficult but geometrically impossible as traveling into yesterday. Nothing marks it. You would cross it without any sensation at all, and only afterward would there be no return. The 47th fact is that the mathematics of that boundary was worked out in 1916 by a German astronomer named Karl Schwarzschild, who solved Einstein's brand new equations of gravity while serving on the Russian front in the First World War. He sent his solution to Einstein from the trenches, and Einstein, surprised that so clean an answer existed at all, presented it to the Prussian Academy. He was 42 years old, and had volunteered for military service despite being well past the usual age. Schwarzschild died of illness a few months later, never knowing what his solution would come to mean. The first description of a black hole was written by a soldier, in a war, in the mud, in the winter. The 48th fact is that supermassive black holes have a curious and rather counterintuitive property, which is that their average density is remarkably low, because the horizon grows in direct proportion to the mass, while volume grows as the cube of the radius. The bigger a black hole becomes, the more thinly its mass is spread within its own boundary. Work out the numbers for Sagittarius A-star and you find an average density not far from that of ordinary air, and for the truly giant ones, thinner than the best vacuum. The largest black holes are, in a strange sense, the emptiest things there are. The 49th fact is that what lies at the very center of Sagittarius A-star, beneath the horizon, is a question our physics cannot presently answer. Einstein's equations, followed all the way inward, predict a singularity, a point where density becomes infinite and the curvature of space becomes infinite too, and where the equations themselves stop meaning anything. Most physicists expect that a future theory of quantum gravity will replace that infinity with something finite and sensible. Most physicists take that infinity not as a description of reality, but as a sign that the theory has reached its limit. Something is there. We simply do not yet have the language for it, and honest ignorance is a kind of peace. The 50th fact is that the simplest way to understand a black hole is through the old idea of escape velocity, the speed at which you must leave a world in order never to fall back. From the Earth, that speed is about 11 kilometers each second. The idea is older than relativity itself and was first sketched out in the 1700s. From the Sun's surface, it is 600. Squeeze any object smaller and denser and its escape velocity climbs, and if you squeeze it enough, the required speed passes 300,000 kilometers each second, the speed of light itself. At that moment, light can no longer leave, and the object has quietly closed itself off from the universe. The 51st fact is that if you were to fall towards Sagittarius A-star, the moment of crossing the event horizon would be entirely uneventful, which is one of the eeriest facts in all of physics. There would be no barrier, no jolt, no flash of light, nothing whatever to mark the passage. Nothing local would ever tell you that the geometry around you had quietly changed its character forever. Space would look strange around you, the sky compressed into a shrinking window overhead, but locally everything would feel perfectly ordinary. You would simply drift on, and at some particular instant the possibility of return would have quietly vanished behind you, without your ever having felt it go. The 52nd fact is that a fall into a supermassive black hole would be far gentler than a fall into a small one, and the reason is a matter of stretching. Tidal force, the difference in gravity between your head and your feet, depends on how sharply the pull changes with distance, and near the huge horizon of Sagittarius A-star that change is very gradual indeed. You would cross the boundary entirely intact, unstretched, comfortable. Only much later, deep inside, would the tides finally grow fierce. The great black holes take you whole and unhurried, which is, in its way, a mercy. The 53rd fact is that time itself runs differently near a black hole, more slowly the closer one approaches the horizon. This is not an illusion or a trick of measurement, but a genuine feature of the universe, tested many times over with atomic clocks flown in aircraft and satellites. Satellite navigation systems must correct for this effect continually, or they would drift badly and quickly wrong. If someone were falling towards Sagittarius A-star while you watched from far away, you would see their descent grow slower and slower, their light redder and dimmer, their motion approaching a standstill that never quite arrives. To your eyes, they would never finish falling. They would simply fade, forever at the edge. The 54th fact is that just outside the event horizon lies a strange region called the photon sphere, at about 1.5 times the Schwarzschild radius. There, gravity bends the path of light so exactly that a beam can travel in a complete circle around the black hole and return to where it began. It is a thin shell made purely of light, and it gives every black hole its bright outlining ring. Light caught their orbits briefly like a moon. It is an unstable balance, and any nudge sends the beam either spiraling inward or escaping outward. But it is real, and it is why a black hole seems ringed by a thin, bright circle, light going round and round. The 55th fact is that matter cannot orbit a black hole all the way down to the horizon, for below a certain distance no stable circle exists at all. Astronomers call that limit the innermost stable circular orbit, and for a slowly turning black hole it lies at about 3 times the Schwarzschild radius. A rapidly spinning black hole draws that limit inward, far closer to the horizon than a still one would. Inside it, any orbit decays, and matter spirals inward with no possibility of settling. It is the edge of the shore, the last place where something can circle in peace. Everything beyond it is committed, and everything within it is already quietly falling. The 56th fact is that Sagittarius A-star is almost certainly spinning, though how fast remains genuinely uncertain. A rotating black hole drags the very fabric of space around with it, a strange effect called frame dragging, in which nothing near the hole can hold still even in principle. Different measurements of our black hole have suggested different spin rates, some slow and some fast, and the question is not yet settled. The evidence from the first images leans toward a moderate spin, tilted so that we look down upon it nearly face a great slow top turning in the dark. The 57th fact is that a black hole is, in a strict sense, the simplest object in the universe, describable completely by only 3 numbers: its mass, its spin, and its electric charge. In practice, any electric charge is neutralized almost at once, so only mass and spin ever really matter. Nothing else survives. Physicists put this famously as the statement that black holes have no hair, meaning no bumps, no features, no memory of what fell in. 2 black holes of the same mass and spin are identical in every way, whether one formed from stars and the other from clouds of gas. All that variety is erased at the horizon, leaving only 3 plain numbers behind. The 58th fact is that as supermassive black holes go, ours is on the modest side, and that becomes plain the moment you compare it with others. The black hole at the center of the galaxy known as M87, the very first one ever imaged, holds about 6.5 billion solar masses, some 1,500 times more than ours. This portrait, released 3 years earlier, made it the first black hole that anyone had ever photographed. Its event horizon is wider than our entire solar system, and there are heavier ones still in the great galaxies at the centers of clusters. Ours is a comfortable, middle-sized creature by comparison. A quiet neighbor, not a monster. The 59th fact is that for all its enormous weight, Sagittarius A-star makes up only a vanishingly small fraction of the mass of the Milky Way as a whole. Our galaxy contains something like 1 trillion solar masses of stars, gas, and unseen dark matter. Most of the galaxy's mass is dark matter, a substance that no one has yet managed to identify. 4 million of that is roughly 1 part in a quarter of a million, a rounding error in the galactic budget. The black hole does not hold the galaxy together, and never did. Its gravity rules only the innermost few light years. Beyond that small realm, the Milky Way turns for reasons entirely its own. The 60th fact is that when you set all these numbers side by side, for million suns, a boundary 17 suns wide, a fall that takes 80 seconds to cross, they resolve at last into a single simple image, a dark, round, silent sphere turning slowly, holding an unimaginable weight in a space smaller than a planet's orbit. It is not chaotic. It is not violent. It is one of the calmest and most orderly things in all of nature, obeying 3 plain numbers and nothing more. Let that quiet, perfect simplicity settle in your mind now, and rest against it. The 61st fact is that the strongest and most beautiful evidence for Sagittarius A-star does not come from seeing the black hole at all, but from watching a small swarm of stars that dance around it. Astronomers call them the S-stars, and there are a few dozen of them. Bright blue suns crowded into a region less than a light year across, sweeping around the galactic center on long looping paths. Their orbits are the closest thing we have to a direct scale drawing of the black hole itself. They move fast enough that their motion is plainly visible from year to year. Watch them long enough and their orbits trace out, in empty space, the shape of something enormous and unseen. The 62nd fact is that the most famous of these is a star called S2, known to another team of astronomers as S0-2. And it has become the single most closely watched star in all of astronomy. It is a hot blue star, perhaps 15 times the mass of our Sun, and it happens to travel on an orbit that brings it startlingly close to the black hole. The 2 different names come from 2 rival teams, each keeping its own catalog of the very same stars. For 30 years now, every clear night has been an opportunity to mark its position a little more precisely. No other star anywhere has been measured so often or so carefully, night after night, decade after decade. The 63rd fact is that S2 completes one full orbit around Sagittarius A-star in about 16 years, which is a remarkably short time for something so vast. It means that astronomers who began watching it as graduate students have now seen it go all the way around, and around again. 16 years is roughly the length of an early scientific career, and several were spent entirely on this. That completeness matters enormously. A partial arc can be fitted by many different shapes, but a closed, repeating ellipse pins the geometry down beyond argument. Watching a whole orbit close upon itself was the moment the case became airtight. 16 years of patience, rewarded by a curve that met itself. The 64th fact is that at the closest point of its long ellipse, S2 sweeps to within about 120 astronomical units of the black hole. An astronomical unit is the distance from the Earth to the Sun, so that is 120 times our own distance from our star. It sounds like a great gulf, and by human standards it is, roughly 4 times as far out as Neptune wanders from the Sun. But for something holding 4 million solar masses, that is a very close pass indeed. Near enough for the star to feel the strangeness of the place. The 65th fact is that as S2 whips through that closest point, it is traveling at about 7,650 kilometers every second, which is roughly 2.5% of the speed of light. Relativity begins to matter noticeably at such speeds, and the measurements now reflect that plainly. Nothing else we can watch so directly moves so fast. In a single second, it crosses more than the width of the Earth 600 times over. At that moment, it is not so much orbiting as being flung around a corner, and the whole passage lasts only a matter of months before it climbs slowly back out again, into the long, cold, patient arc of its year. The 66th fact is that the shape of S2's path is a very long, drawn-out ellipse, a great stretched oval rather than a comfortable circle. At its farthest, the star drifts nearly 1,000 astronomical units from the black hole, moving slowly and quietly through the cold dark. The eccentricity of its orbit is about 0.9, which is a very stretched shape indeed. Then, gathering speed as it falls, it comes rushing inward for its brief and violent close pass, and swings away again. It is exactly the shape a comet traces around our sun, only vastly larger and vastly faster. The same simple law of gravity draws them both, on scales that could hardly be more different. The 67th fact is that mapping these orbits required an almost inhuman constancy of purpose, because the motions, though fast, are tiny when seen across 26,000 light-years. Astronomers had to measure positions to a few thousandths of an arc-second, again and again, through the shimmer of the atmosphere and the crowding of neighboring stars, for decades on end. The whole orbit spans less than a quarter of an arc-second as we see it on the sky. Each night's work added a single point to a curve that would take a generation to draw. There were no shortcuts and no dramatic breakthroughs, only accumulation, one measurement at a time, patiently gathered until the shape of the invisible finally appeared. The 68th fact is that one of the 2 teams that did this work was led by the German astrophysicist Reinhard Genzel, using telescopes of the European Southern Observatory in the Atacama Desert of Chile. He began in the early 1990s with speckle imaging on a smaller telescope, then moved to the great 8-meter mirrors of the Very Large Telescope as they came online, and finally to the exquisite precision of the gravity instrument. Across 30 years, he never let the project go. The whole discovery is, in large part, a record of one group refusing to look away. The 69th fact is that the other team was led by the American astronomer Andrea Ghez, working with the 10-meter Keck telescopes on the high summit of Mauna Kea in Hawaii. She pushed hard for adaptive optics and laser guide stars, and her group produced independent measurements of the very same stars, using different instruments, different software, and different assumptions. The guide star system on those telescopes fires a beam of orange laser light into the upper atmosphere. That independence was priceless. When two entirely separate teams, half a world apart, arrived at the same orbits and the same mass, the results stopped being a claim and became a fact, confirmed twice over. The 70th fact is that the relationship between those two groups was a long and famously spirited rivalry, competitive but honest, and science was much the better for it. Each checked the other's work with a sharp and skeptical eye. Independent confirmation is the quiet machinery by which science protects itself from its own enthusiasm. Each raced to publish first. Each was forced by the other's scrutiny to be more careful than it might otherwise have been. In the end, the two sets of orbits agreed beautifully, and the two leaders shared the same prize. It is a lovely example of how disagreement, pursued in good faith, arrives at truth more reliably than agreement ever could. The 71st fact is that in the year 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for the discovery of a supermassive compact object at the center of our galaxy. They shared the prize with the British mathematician Roger Penrose, honored for showing that black hole formation is a robust prediction of general relativity. The ceremony that year was held remotely, in the strange and echoing quiet of a pandemic winter. It was, in a sense, a prize for the whole idea of black holes, from the theory that made them inevitable to the observations that found one in our own back garden. Theory and evidence honored together. The 72nd fact is that Andrea Ghez became only the fourth woman in history to receive the Nobel Prize in Physics. Following Marie Curie, Maria Goeppert-Mayer, and Donna Strickland, she has spoken often about how much of the work was simply refusing to accept blur, insisting that better instruments could be built and that the sky could be seen more sharply than anyone had managed. She grew up watching the Apollo landings and deciding at 4 years old to be an astronaut. She became something rarer instead, the person who first weighed the heart of the galaxy. The 73rd fact is that Roger Penrose's contribution came much earlier, in 1965, and was purely a work of mathematics. At the time, many physicists suspected that black holes were an artifact of idealized, perfectly symmetric calculations, and that any realistic, messy collapse would somehow avoid them. His methods were so novel that many physicists needed years simply to learn how to follow the argument. Penrose proved otherwise. Using elegant new geometric methods, he showed that once a certain surface forms, a singularity must follow, symmetry or no symmetry. Black holes were not a special case. They were a general and unavoidable consequence of gravity, written into the structure of space and time. The 74th fact is that the deepest meaning of the S-star orbits is that they close upon themselves as ellipses with the black hole at one focus, exactly as Kepler's laws demand for a single compact mass. That geometry rules out almost every alternative. The focus of an ellipse is a single point, and a point is very nearly what a black hole is. A dense cluster of ordinary stars would produce different rosette-like paths. A cloud of dark matter would spread the pull-out and change the shape entirely. Only a point, or something very nearly a point, produces those clean, repeating ovals. The stars, in their dancing, drew the answer in the sky for us. The 75th fact is that during S2's close pass in 2018, astronomers detected something Einstein predicted more than a century ago, a shift in the star's light called gravitational redshift. Climbing out of the deep well of the black hole's gravity costs light energy, and light that loses energy grows redder. It is the same effect that reddens light climbing out of the Earth's own gravity, only vastly stronger. The effect was small, a change of just a few thousandths of a percent in wavelength, but it was measured cleanly and it matched the prediction exactly. General relativity had been tested in a place no one could have dreamed of when it was written. The 76th fact is that 2 years later, the same teams measured something subtler still, a slow rotation of S2's entire orbit called Schwarzschild precession. Rather than tracing the same ellipse forever, the star's path turns a little with each circuit, so that over many orbits it sketches a slowly opening rosette. It is precisely the effect that first vindicated Einstein with the planet Mercury, only here it is vastly stronger. Watching an orbit fail to close in exactly the way relativity predicts is a strange and quiet thrill. The universe, keeping its promises. The 77th fact is that the S-stars pose a real and unsolved puzzle, which astronomers have nicknamed the paradox of youth. These are hot, massive, blue stars, and such stars live only a few million years. One idea is that binary stars are torn apart nearby, leaving a single member captured in a tight orbit. Yet they sit in a place where the black hole's tides should tear apart any gas cloud long before it could collapse into a star. They should not have been born there, and they have not had time to travel there from anywhere else. Something is bringing them in, or forming them in ways we do not yet understand. A mystery still open. The 78th fact is that S2, famous as it is no longer the record holder, for astronomers have since found stars on even tighter and swifter paths. One, called S62, races around in roughly 10 years. Each closer and faster star tests relativity in a stronger gravitational field than the last one did. Another, catalogued as S4716, appears to complete an entire orbit in only about 4 years, sweeping in to within 1/100th of a light-year of the black hole. Each new discovery pushes the measurements finer and the tests of relativity sharper. The innermost dancers are still being found, one by one, as our instruments grow patient enough. The 79th fact is that if you could somehow stand upon a world circling one of these stars, the sky above you would be like nothing any human has ever seen. Thousands of brilliant suns would crowd the darkness, so many that the night would glow. The bending of starlight around that region would be plainly visible to the unaided eye. And in one direction there would be a strange region of sky where the stars behind seemed to bend and slide and double, warped smoothly around a small perfect circle of absolute black. You would see no object there. You would see only the sky gently rearranged around something that was not there at all. The 80th fact is that there is something almost tender in the image of those stars, wheeling patiently in the dark around a partner they cannot see and will never touch. For millions of years they have traced their long ellipses, rushing in, sweeping past, drifting slowly out again, held in place by nothing visible whatsoever. They do not fall in. They simply circle faithfully on and on. As you settle deeper towards sleep, you might hold that picture in your mind. A slow, silent dance in the heart of the galaxy, going on quietly all night long. The 81st fact is that on the 12th of May, in the year 2022, humanity saw the heart of its own galaxy for the very first time. At simultaneous press conferences held around the world, the Event Horizon Telescope collaboration unveiled an image of Sagittarius A-star, a soft orange ring of light with a round darkness at its center. The announcement was carried live in 7 languages, from 6 cities, at the very same hour. After 90 years of listening and 30 years of watching stars circle in emptiness, there it finally was in a photograph. It is a quiet, blurry, unremarkable-looking picture, and it is one of the most extraordinary images ever made. The 82nd fact is that the Event Horizon Telescope is not a telescope in any ordinary sense, but a worldwide collaboration of more than 300 scientists from dozens of countries and institutions They agreed to point their separate instruments at the same targets on the same nights, to record their data in precisely the same way, and to combine everything afterward into a single result. Agreements of that kind are rare in science, and they take years of quiet diplomacy to arrange. No one country could have done it. No one observatory could have done it. It required an unusual and rather beautiful willingness to share telescopes, data, credit, and years of careful work. The 83rd fact is that the observations that produced the image were made in April of 2017, using 8 radio observatories scattered across the Earth. There were dishes in Arizona and in Mexico, in Spain and in Hawaii, in Chile in the high Atacama, and at the South Pole itself. The weather at all 8 sites had to cooperate on the same nights, which is no small demand. Together they spanned nearly the full diameter of the planet. Each one recorded the faint millimeter-wave glow from the galactic center, while atomic clocks marked the arrival of every wavefront to a precision of billionths of a second, 8 ears, listening as one. The 84th fact is that when those 8 sites are combined, they behave as a single telescope the size of the Earth, and that is the whole trick of it. The sharpness of any telescope depends on its width compared to the wavelength of the light it gathers. So to see something impossibly small, you need an impossibly large instrument. Building a dish 12,000 kilometers wide is out of the question. But building 8 dishes and separating them by that distance is merely very difficult. The Earth itself became the lens, turning slowly, filling in the picture as it went. The 85th fact is that Sagittarius A-star, seen from Earth, spans an apparent size of only about 52 microarcseconds. A microarcsecond is a millionth of 1 arcsecond, and an arcsecond is already a 3,600th of a degree. That is roughly the angle a single human hair would subtend from 10,000 kilometers away. The usual comparison is that resolving it is like picking out a donut sitting on the surface of the moon, or reading the date on a coin in Los Angeles from a chair in New York. It is the largest black hole shadow in our sky, and it is still almost immeasurably tiny. A donut on the moon. The 86th fact is that what the image actually shows is a bright, slightly uneven ring of light surrounding a dark central region. And the darkness is the point of the whole thing. That shadow is where light has fallen in and never come back out. You cannot photograph a black hole. You can only photograph the light it happens to fail to keep. The ring is hot gas glowing furiously just outside, its light bent around the hole by gravity into a circle. The picture is not of the black hole itself, for a black hole has nothing to show. It is a portrait of an absence, drawn, gently, by the light that outlines it. The 87th fact is that the dark shadow in the image is considerably larger than the event horizon itself, by a factor of about 2.5. The reason is that gravity bends the paths of light rays near the hole, so that beams which would otherwise pass safely by are curved inward and swallowed. The predicted ratio was worked out theoretically decades before anyone could seriously hope to test it. From far away, the region that appears black therefore extends well beyond the true boundary. It is a little like the way a glass of water makes a straw look broken. The shape we see is the shape of bent light, not of the object. The 88th fact is that the amount of data gathered by those 8 observatories was so enormous that it could not be sent over any network on Earth. Each site recorded several petabytes of raw signal, filling entire racks of hard drives, and the only practical way to bring it together was to pack the drives into crates and put them on airplanes. 1/2 ton of hard disks flew to Massachusetts and to Germany, where specialized supercomputers waited to combine them. The most advanced image in astronomy traveled by cargo flight, a modern discovery delivered by freight. The 89th fact is that the data recorded at the South Pole could not be shipped at all until the Antarctic winter had ended, and no aircraft can land there for months on end. So while the rest of the world's recordings arrived and waited, the polar drives sat in the dark and the cold, holding a piece of the picture that no one could yet see. The last of those drives arrived in December, more than half a year after the observations were made. They finally flew out at the end of the season, months later. The image of our galaxy's heart was quite literally incomplete, until the ice let it go. The 90th fact is that even once all the data had arrived, the work of turning it into a picture took 5 more years of careful analysis. The signals from each pair of telescopes give only a fragment of the information a real image would contain, and the missing pieces must be filled in by inference, with great care taken not to invent anything. Restraint of that kind is unglamorous work, and it is precisely what makes the final result trustworthy. For separate teams worked independently, kept deliberately apart so that none could influence the others. Only when all 4 produced the same ring by different methods was anyone willing to believe it. The 91st fact is that Sagittarius A-star proved far harder to photograph than the first black hole ever imaged. And the reason is simply that ours is small and quick. Gas orbits our black hole in a matter of minutes, so the pattern of brightness changes visibly while the telescopes are still observing. The gas nearest our black hole completes an entire circuit in only a handful of minutes. It is like trying to take a long exposure of a puppy. The much larger black hole in M87 changes over days and sits obligingly still. Ours flickers and shifts all night, which is why it came second despite being nearer. The 92nd fact is that the solution to that flickering was to accept it, and to make not one image but thousands. The teams generated an enormous library of possible pictures consistent with the data, then sorted them into families by their common features. The great majority across every method showed a ring of very much the same size. So the published image is not a single snapshot at all but an average, a portrait of what the black hole looks like on the whole rather than in any one instant. The shape beneath the shimmer. The 93rd fact is that the very first image of any black hole came 3 years earlier, in April of 2019, and showed the giant at the center of the galaxy M87, some 55 million light-years away. That picture stunned the world. A soft asymmetric orange ring around a dark hollow. That first orange ring appeared on the front pages of newspapers in every country in the world. It was, in a sense, a rehearsal. Everything the collaboration learned from that first success was carried forward. When they turned at last to our own galaxy, they knew exactly what they were doing, and exactly what to look for. The 94th fact is that the ring in the image of Sagittarius A-star is not uniformly bright, but shows 3 somewhat brighter patches around its circumference. Some of that unevenness is genuine, caused by hot gas piled up in particular places and by the way motion toward us brightens light while motion away dims it. Brightness on the approaching side is boosted by the motion itself, an effect called relativistic beaming. Some of it may be an artifact of the sparse data. Astronomers are still working out how much of that pattern is real. But an uneven ring is exactly what theory predicted, and finding it there was quietly satisfying. The 95th fact is that the image suggests we are looking at Sagittarius A-star very nearly face-on, gazing almost straight down its axis of rotation. That is a fortunate accident of geometry. That orientation also happens to match what the orbiting hotspots had already quietly suggested. Had we seen it edge-on, the ring would appear squashed and strongly lopsided, much harder to interpret. Instead, we get the clean, round, almost symmetrical view. Out of all the possible orientations in which our galaxy's black hole might have presented itself, we happen to have drawn one of the clearest, a small piece of good luck, 26,000 light-years wide. The 96th fact is that the algorithms which turned scattered radio measurements into a picture were developed by a large team of imaging specialists, among them a young computer scientist named Katie Bauman. Her work on reconstruction methods, and on testing them rigorously against false results, became widely known when the first image was released. The essential problem she and her colleagues addressed was how to fill in missing information without accidentally drawing what you expect to see. Their answer was to test every method against everything it must not produce, and to trust only what survived. The 97th fact is that the size of the ring in the photograph matched, almost exactly, the size predicted from the orbits of the S-stars, and that agreement is quietly thrilling. Two utterly different methods, one watching stars move over decades in infrared light, the other combining radio waves across the Earth, arrived at the same mass and the same horizon. Two roads, one built of infrared light and one of radio waves, arrived at exactly the same doorstep. Neither depended on the other. When independent roads lead to the same place, you may be fairly confident the place is real. That is how certainty is actually built, by agreement between strangers. The 98th fact is that the warm orange color of the famous image is not real, and was chosen by human beings. The observations were made in millimeter radio waves, far outside anything our eyes can perceive, and such data have no color at all in the ordinary sense. Radio astronomers routinely choose their colors the way a mapmaker chooses them, for clarity and nothing else. The team selected a soft, warm palette because it seemed to suit the object and to read clearly to the public eye. Had they chosen blue or green or gray, the picture would be equally true. The shape is the science. The color is a courtesy. The 99th fact is that the glowing ring itself is made of gas so hot that it has been stripped into a plasma of free electrons and bare nuclei, spiraling through fierce magnetic fields. As those electrons wind around the field lines at nearly the speed of light, they radiate, and it is that radiation which the telescopes gather. This kind of glow is called synchrotron radiation, and it appears wherever magnetism meets very fast particles. So the light in the image was made by individual particles, dancing in a magnetic web just outside the edge of the world. It is very hot, very thin, and very old light, arriving quietly at last. The 100th fact is that we are the first generation of human beings ever to have seen a picture of the center of our own galaxy, and every generation after us will simply grow up with it. For all the hundreds of thousands of years that people have looked up at the summer Milky Way, no one knew what lay behind it. Now there is a photograph, taken in our lifetime, of the quiet dark thing at the heart of our home. As you drift now towards sleep, you might simply hold that soft orange ring in your mind and let it glow there gently. The 101st fact is that the single most surprising thing about Sagittarius A-star, to the astronomers who study it, is how astonishingly dim it is, a black hole of 4 million solar masses, sitting in the gas-rich heart of a galaxy, ought by every naive expectation to blaze. That faintness was for many years considered one of the outstanding unsolved problems of the field. Instead, it glows more faintly than many ordinary stars. If you added up all the light it produces across every wavelength, it would amount to only a few hundred times the output of our sun, which for an object of its size is essentially nothing at all. Our galaxy's heart is, in the plainest terms, extraordinarily quiet. The 102nd fact is that astronomers measure this quietness against something called the Eddington limit, which is the brightest a feeding black hole can be before its own radiation blows away the gas trying to fall in. It is a natural ceiling, set by the balance between gravity pulling inward and light pushing outward. The limit is named for Arthur Eddington, who worked it out in the 1920s. For a black hole of 4 million solar masses, That ceiling is enormously high, hundreds of billions of times the sun's output. Sagittarius A-star runs at something like 1/1000th of that limit, a furnace idling at the very lowest possible setting. The 103rd fact is that the reason for the dimness is simply that Sagittarius A-star is barely eating at all. The gas available to it in the innermost region amounts to only a trickle, and even that trickle mostly fails to arrive. Even a single modest comet, delivered whole, would represent an unusually generous meal for it. Estimates suggest it actually swallows somewhere around 100 millionth of a solar mass in a year, which is roughly the mass of a small asteroid every day. Set against 4 million suns already inside, that is less than nothing. It is a creature the size of a mountain, living on a few crumbs, and not even hungry for more. The 104th fact is that a great deal of gas does approach Sagittarius A-star, far more than it ever consumes, and understanding what happens to the rest took decades of work. The winds of nearby massive stars pour a steady supply of material inward, enough to feed a far brighter black hole. But almost all of it turns back. Only about 1% or less of the gas that reaches the outer edge of the flow ever crosses the horizon. The rest is heated, stirred, and thrown back out into the surrounding dark, arriving, and then quietly leaving again. The 105th fact is that the gas near Sagittarius A-star does not form the neat, thin, glowing disk that most people picture around a black hole. At such low densities, the plasma cannot cool efficiently, and so instead of settling into a flat platter, it puffs up into a thick, hot, slowly swirling cloud. Such a flow carries most of its heat inward across the horizon rather than radiating it away into space. Astronomers call this a radiatively inefficient accretion flow, which is a long name for a simple idea that the gas heats up and holds onto its heat rather than radiating it away. The energy goes into motion and turbulence rather than into light, which is precisely why we see so little. The 106th fact is that much of the gas that fails to fall in is driven back outward as a slow, hot wind. Observations with X-ray telescopes have found evidence for exactly such an outflow, carrying material away from the black hole faster than it can be swallowed. The outflow was inferred from the shape and temperature of the faint X-ray glow around the central region. It is a self-regulating arrangement, in a way, the black hole quietly refusing most of what is offered to it. There is a certain temperance in this. It could gorge and blaze and blast the inner galaxy with radiation. It simply does not, and has not for a very long time. The 107th fact is that Sagittarius A-star is not entirely still, however, for it flares. Roughly once a day, the Chandra X-ray Observatory catches a sudden brightening from the black hole's position, a flash that rises and fades over an hour or two before settling back into its usual faint glow. Chandra has returned to watch it in almost every year since the observatory was first launched. These flares are among the few ways it announces itself. They are gentle by cosmic standards and utterly harmless at our distance, but they tell us that something is happening down there. The great quiet is not perfect. Every so often, something stirs. The 108th fact is that in infrared light the flaring is even more frequent, with several noticeable brightenings each day, and the source is essentially never entirely at rest. Careful monitoring shows a continuous low flickering, rising every so often into a clear flare. Astronomers have watched for statistical patterns in the timing and found the flares arrive at random, with no clock behind them. They are like the crackling of a very slow fire, unpredictable in any single instance yet reliable in the long run. A steady, gentle irregularity going on all the time. The 109th fact is that the strongest flares can brighten Sagittarius A-star by a factor of 100 or more, though even then it remains dim by any reasonable standard, In 2019, astronomers recorded the brightest infrared flare ever seen from it, so unusual that they at first suspected an instrumental fault. Even that record-breaking flare would have remained entirely invisible to the unaided eye from any distance at all. Even so, at that peak it was still shining far below what a well-fed black hole would produce continuously. Its most dramatic outbursts are, by the standards of its kind, no more than a small shrug in the dark. The 110th fact is that the most likely cause of the flares is magnetic reconnection, the same process that drives flares on the surface of our own sun. In the hot plasma swirling near the black hole, magnetic field lines become twisted and tangled by the motion of the gas, storing energy the way a wound spring does. The very same physics powers the auroras that light the polar skies of our own small planet. When those lines snap and reconnect into a simpler arrangement, the stored energy is released all at once, accelerating particles to enormous speeds. The result is a burst of light. The heart of the galaxy flares for the same reason a sunspot does. The 111th fact is that in 2018, the gravity instrument in Chile watched something remarkable during 3 separate flares. It saw the point of emission move, tracing a small circular loop on the sky over the course of the flare. 3 separate flares produced 3 loops, all turning in the same direction and all very nearly the same size. Something bright was orbiting the black hole, and the astronomers were watching it go around. It was the first time anyone had directly followed material circling so close to an event horizon. A hot spot, born in the plasma, swinging round and visible faintly from 26,000 light-years away. The 112th fact is that each of those orbiting hotspots completed a full circle in something like 45 minutes, moving at roughly 30% of the speed of light. Think of that for a moment. A blob of glowing plasma, going around an entire black hole in less time than it takes to watch a television program, at a third the speed of light. The circle it traced was only a few times wider than the event horizon itself. Nothing in astronomy happens so fast, so close, and so visibly, and we simply watched it happen. The 113th fact is that the size of those orbits tells us the hot spots were forming near the innermost stable circular orbit, the last place where matter can circle in peace. That is the boundary of the region we can never see into, the doorstep of the horizon. Below that particular boundary there is no more circling to be done, only descent. Material there is on the very edge of committing itself. Some of it eventually spirals in and is lost. Some of it is flung back out. The flares are, in a sense, the sound of that decision being made, over and over, all day, every day. The 114th fact is that the plasma around Sagittarius A-star appears to be strongly magnetized, so strongly that the magnetic field itself may be holding back the flow of gas. Astronomers call this state a magnetically arrested disk, a condition in which the field piles up near the black hole until it pushes outward as hard as gravity pulls in. Computer simulations of such magnetically choked disks reproduce the observed dimness rather well. Matter then leaks inward only in fits and starts, in fingers and blobs rather than a smooth stream. It may be a large part of why the black hole eats so little. A magnetic gate half closed. The 115th fact is that Sagittarius A-star does not appear to have a great jet, and that absence is itself interesting. Many feeding black holes, including the one in M87, launch narrow beams of plasma outward for thousands of light-years, visible across the universe. Jets are thought to draw their enormous power from the spin of the black hole itself. Ours shows no such thing today, despite careful searching. There may be a small, weak outflow near the center, but nothing grand. Perhaps it needs to be feeding more heavily to build one. Whatever the reason, The great engine of our galaxy is not currently pointing anything at anyone. The 116th fact is that what little food Sagittarius A-star receives comes largely from the winds of the massive young stars orbiting nearby. Those hot blue giants shed their outer layers steadily into space, and some of that material drifts inward and joins the swirling flow. It is an oddly domestic arrangement, a black hole living on what its neighbors happen to blow its way. If those stars were not there, it would be quieter still. In a few million years, when they die, the supply may change, and the heart of the galaxy will change with it. The 117th fact is that the gas in the innermost region reaches temperatures of billions of degrees, hotter than the core of any star, and yet it is so extraordinarily thin, far thinner than the best vacuum ever produced in a laboratory, that it holds almost no heat in any everyday sense. Densities there amount to perhaps a few particles in every cubic centimeter, and often considerably fewer. Temperature in such a plasma means only that individual particles are moving at furious speeds, not that there is much energy in a given volume. It is scorchingly hot and almost perfectly empty at the same time. A fierce, ghostly, nearly non-existent fire. The 118th fact is that all of this, the flaring and the swirling and the falling, happens in absolute silence. There is no air out there to carry sound, no medium to vibrate, nothing to hear. Even the great merger of two black holes would pass in total, perfect, unbroken silence. The hot spots race around at a third the speed of light without the faintest whisper. The great magnetic snapping releases its energy soundlessly. Whatever we may imagine about the drama of a black hole, the truth is that the center of our galaxy is one of the quietest places imaginable, perfectly, completely, endlessly still. The 119th fact is that among all the supermassive black holes we know of, ours is one of the most subdued relative to its size, and that has almost certainly been true for a very long time. There are galaxies where the central black hole pours out more light than every star around it combined. Astronomers sometimes describe our galaxy as a quiet, ordinary, middle-aged spiral, and that description is quite fair. There are others where jets carve enormous cavities in the surrounding gas. Ours simply turns and glimmers and waits. We happen to live in a galaxy whose heart went quiet long ago, and has stayed that way. The 120th fact is that as you lie here now, at this very moment, 26,000 light-years away, that faint flickering is going on. A little gas is spiraling inward. A magnetic field is slowly twisting. Somewhere a hot spot is beginning its 45-minute journey around the edge of the dark. It is happening quietly, without hurry, and without the slightest awareness of us. There is something profoundly restful in that thought, that the heart of the galaxy is simply carrying on, unbothered, all through the night, exactly as it has for ages. The 121st fact is that Sagittarius A-star does not sit alone in empty space, but at the very center of an immense swarm of stars that astronomers call the nuclear star cluster. It contains something like 20 or 30 million solar masses of stars, packed into a region only a few light-years across, and it is one of the densest and most massive star clusters known anywhere. Similar clusters sit at the centers of most spiral galaxies, though very few of them are so near to us. The black hole is embedded in it like a stone in the middle of a great luminous nest. Where we live, stars are scattered thinly. There they are heaped together, shoulder to shoulder in the dark. The 122nd fact is that in the innermost parsec of the galaxy, the density of stars is something like 100 million times greater than in our own quiet corner. Where our nearest stellar neighbor lies more than 4 light-years away, stars there may be separated by a few thousand astronomical units, close enough that they occasionally disturb one another's orbits. Nothing in our own sky prepares the imagination for a crowd packed together at such a density. Encounters that would take 100 billion years out here happen there in a few million. It is a place of constant gentle jostling. A crowd, slowly rearranging itself over the ages. The 123rd fact is that if you lived on a world within that cluster, you would never truly know darkness. Thousands of stars would shine more brightly than Venus does for us, and 100 or more would be brighter than the full moon. The nearest stars would be close enough to show as tiny disks rather than as simple points of light. The whole sky would glow softly, the ground faintly lit at every hour, the shadows soft and many-directioned. There would be no Milky Way to see, because you would be inside its brightest part. Astronomy there would be nearly impossible, and yet the nights would be indescribably beautiful. The 124th fact is that surrounding all of this, spanning several hundred light-years, is a vast reservoir of dense, cold gas that astronomers call the central molecular zone. It holds perhaps 60 million solar masses of molecular gas, a substantial fraction of all the molecular material in the entire galaxy, crammed into a tiny fraction of its volume. The clouds there are denser, hotter, and more turbulent than anywhere else we know. It is from this great reservoir that the whole galactic center is fed. A slow, cold, enormous larder, ringing the heart of the Milky Way. The 125th fact is that one particular cloud in that region, called Sagittarius B2, is among the most chemically rich places in the known universe. Radio astronomers have detected within it an astonishing catalog of molecules, dozens upon dozens of different compounds, including many complex organic ones that were never expected to survive in space at all. New molecules are still being discovered within it, several of them in most years. Sugars have been found there, so have the simplest building blocks associated with life's chemistry. It is a great cold cathedral of chemistry, quietly assembling complicated things in the dark, just a few hundred light-years from the black hole. The 126th fact is that among the molecules found in Sagittarius B2 are ethyl alcohol and ethyl formate, which is the compound that gives raspberries much of their flavor and rum much of its smell. The discovery gave rise to a great many cheerful headlines about a cloud of raspberry-flavored rum drifting through the galaxy. The molecules are spread far more thinly there than in the very best laboratory vacuum on Earth. The truth is more modest, of course, since the molecules are spread so thinly that no one could ever gather them. But it is charming and quite real that the heart of our galaxy smells faintly, in principle, of raspberries. The 127th fact is that immediately around Sagittarius A-star, beginning at about 1.5 light-years out, there lies a ring of dense gas and dust known as the circumnuclear disk. It is a thick, clumpy torus, tilted and turning, extending outward for perhaps 7 light-years, and it marks the inner edge of the cold material that surrounds the black hole. Its inner edge is remarkably sharp, and nobody is entirely certain why that should be so. Inside its central hole lies the hot, thin, ionized region where the S-stars dance. The black hole sits at the middle of a great slow smoke ring, quietly at the center of everything. The 128th fact is that within a few dozen light-years of the black hole sit two extraordinary young star clusters, called the Arches and the Quintuplet. They are among the densest and most massive clusters in the galaxy, brimming with hot blue stars only a few million years old. The Arches cluster alone contains dozens of stars more than 100 times the mass of our Sun. Their fierce winds and radiation carve and light the surrounding gas. In a place where star formation should be difficult, the galactic center has managed it spectacularly. The 129th fact is that the Quintuplet cluster is home to one of the most luminous stars ever discovered, an object called the Pistol Star. It shines with perhaps 1.5 million times the brightness of our sun, and it has already shed an enormous shell of gas that glows around it in the shape which gave it its name. It sheds so much material that it may end its brief life within a few 100,000 years. In a single second, it emits as much energy as our sun does in a year. And yet, from Earth, you cannot see it at all, hidden like everything else there behind the dust. The 130th fact is that in 2013, astronomers discovered a magnetar in orbit around Sagittarius A-star, less than half a light-year from the black hole. It announced itself with a burst of X-rays and has been studied intently ever since. Its discovery was partly a matter of luck, for it happened to flare while telescopes were already watching. It is the closest neutron star to any supermassive black hole ever found, and its existence was entirely unexpected. Finding one so near the center, when so many other searches had come up empty, was both a delight and a puzzle. A small, dense lighthouse circling the dark. The 131st fact is that a magnetar is a kind of neutron star with a magnetic field so strong that it is difficult to describe honestly, perhaps 1,000 trillion times stronger than the Earth's. Its magnetic field is strong enough to make the vacuum of space itself behave rather like a crystal. If one were placed at the distance of the moon, it would erase the data from every credit card on the planet. Its field is strong enough to distort the shape of atoms themselves. These are the most magnetic objects known to exist anywhere in the universe, and one of them is quietly orbiting the heart of our galaxy. The 132nd fact is that this particular magnetar turned out to be scientifically precious, because its radio pulses pass through the plasma near the black hole on their way to us. By measuring how those pulses are twisted and delayed, astronomers could infer the strength and structure of the magnetic field in a region no telescope can resolve. A single accidental object became a probe of the invisible. It is a common pattern in astronomy that the most useful discoveries are the ones nobody was looking for, found by luck and then used carefully. The 133rd fact is that theory predicts something remarkable about the region around Sagittarius A-star, which is that it should be swarming with small black holes. Over billions of years, heavier objects in a star cluster gradually sink toward the center, a process called mass segregation, and stellar mass black holes are among the heaviest things around. Nothing at all about them would be visible, and they would betray themselves only through their gravity. Calculations suggest as many as 10,000 of them may have gathered within a few light-years of the galactic center. They would be dark, silent, and almost impossible to detect. A hidden crowd drifting quietly in the middle. The 134th fact is that in 2018, astronomers found the first real evidence for that hidden crowd. Sifting through years of Chandra X-ray observations, they identified about a dozen faint sources near the galactic center whose properties matched black holes feeding gently on companion stars. Each of those faint systems is a black hole quietly drawing gas away from an unlucky companion star. A dozen visible ones, in a region where only a small fraction would ever be detectable, implies many hundreds or thousands more that are entirely dark. The prediction had stood for decades. The confirmation arrived quietly in a table of faint X-ray sources. The 135th fact is that there is a genuine and unresolved mystery about pulsars near the galactic center, which is that we find almost none, given the number of massive stars there, and how many should have died as neutron stars. Astronomers expected to detect hundreds of pulsars within the inner region. The absence has been named the missing pulsar problem, and it remains a genuinely open question. Long and careful searches have found only a handful. Perhaps the dense plasma scatters their pulses beyond recovery. Perhaps the stars there die differently, Nobody yet knows. It is a plain, stubborn absence. One of the honest, open questions of the field. The 136th fact is that in 2014, astronomers around the world watched with great anticipation as a small cloud of gas, known as G2, swung in towards Sagittarius A-star. It had been discovered a few years earlier on a plunging orbit, and predictions abounded that it would be torn apart and devoured, briefly lighting the black hole up in a spectacular display. Telescopes were booked. Papers were prepared. The closest approach came and went, and almost nothing happened at all. The 137th fact is that the anticlimax of G2 turned out to be more interesting than the fireworks would have been. The cloud stretched somewhat as it rounded the black hole, but it held together, which a simple ball of gas could not have done. Predictions that fail are among the most productive things in the whole of science. The best explanation is that G2 is not a cloud at all but a star, perhaps a pair of stars recently merged, wrapped in a puffy shell of dust and gas. Its own gravity held it intact. The universe declined to perform and taught us something better. The 138th fact is that since then, astronomers have identified a whole small family of similar objects near the black hole. Labeled simply G1, G2, G3, and onward, they look like dusty clouds but behave like stars, and there are now at least half a dozen of them known. They travel on paths quite unlike those of the ordinary stars all around them. They may be the swollen remnants of stellar mergers, driven together by the crowded conditions near the center. Each one is a small mystery. Together they suggest that the galactic center is doing something to stars that we do not yet fully understand. The 139th fact is that the region around Sagittarius A-star is threaded by strange structures called the radiofilaments, and they are unlike anything found elsewhere in the galaxy. They are long, thin, remarkably straight strands of magnetized plasma, some of them 100 light-years long and only a fraction of a light-year wide, glowing in radio light. Nothing remotely comparable has ever been found in any other part of the Milky Way. Hundreds have now been mapped. They appear to be organized by powerful magnetic fields, but why they form there, and only there, remains unclear. Great luminous threads, hanging in the dark, quietly unexplained. The 140th fact is that taken all together, the neighborhood of Sagittarius A-star is the richest and strangest few hundred light-years in the entire Milky Way. A crowded cluster of ancient suns, a ring of cold gas, clouds full of complicated chemistry, magnetars, thousands of hidden black holes, luminous threads of magnetism, and a family of small mysteries still unexplained. And through all of it, everything simply turns, slowly and quietly, around one small dark point. Let that vast, strange, patient neighborhood drift through your mind now, and let it settle you deeper. The 141st fact is that Sagittarius A-star has not always been as quiet as it is tonight. The evidence is now quite clear that in the past it has flared far more brightly, sometimes by enormous factors, and that the sleepy black hole we observe today is a creature resting between meals. Reading a black hole's history requires looking not at the hole itself but at everything surrounding it. Astronomers have found the fingerprints of these old outbursts written in the gas around the galactic center, in the shape of the sky far above the disk, and in the chemistry of clouds hundreds of light-years away. The quiet is real, but it is recent. The 142nd fact is that the most elegant of these clues is something called an X-ray echo, and it works very much like a shout returning off a distant cliff. When the black hole flares, its light travels outward in all directions. Astronomers use the very same trick on exploding stars, watching their light illuminate surrounding dust for years afterward. Most of it vanishes into space, but some strikes the great molecular clouds surrounding the galactic center, and those clouds glow faintly in response. Because that reflected light takes a longer path to reach us, it arrives late, long after the original flash has passed. We hear the echo, though the shout is gone. The 143rd fact is that the echoes we are receiving now suggest that Sagittarius A-star underwent a substantial outburst roughly 200 years ago, around the beginning of the 19th century. At that time, it may have shone something like 1,000,000 times brighter than it does today, blazing briefly before falling silent again. That would place the outburst somewhere around the time of the Napoleonic Wars in Europe. No one on Earth saw it, of course, hidden as it is behind all that dust. But the light of that flare is still traveling outward through the clouds of the galactic center, and we are watching its reflection arrive. The 144th fact is that this method of seeing the past is called light echotomography, and it lets astronomers reconstruct events they entirely missed. Because different clouds lie at different distances, they light up at different times, and by watching which cloud brightens when, astronomers can work backward to the moment and the strength of the original flare. It is a way of using the whole galactic center as a slow, three-dimensional recording device. The past is not gone. It is simply still in transit and reflecting off everything on the way. The 145th fact is that the great cloud Sagittarius B2 has served as the most important mirror in this work. It sits a few hundred light-years from the black hole, dense enough to reflect efficiently and positioned so that its echoes arrive on a convenient schedule. It is one of the most massive molecular clouds to be found anywhere in the galaxy. Over the past 30 years, X-ray telescopes have watched it brighten and fade in patches, as different parts of the cloud caught different portions of the ancient flare. A cold cloud of gas, quietly replaying a 200-year-old flash, over and over, for anyone patient enough to watch. The 146th fact is that the particular signature astronomers look for is a bright emission line from iron atoms, produced when X-rays strike them and knock out an inner electron. The atom immediately rearranges itself and emits a photon of a very specific energy, and that sharp line stands out clearly against everything else. The line comes from iron atoms and appears at one very specific energy in the X-ray band. Its presence in a cold cloud is a plain announcement that intense X-rays passed through recently. It is a fingerprint that cannot easily be faked. The chemistry of iron, quietly cooperating, gave us a window into the black hole's history. The 147th fact is that these echoes can actually be seen to move across the clouds from year to year, which is one of the loveliest observations in all of astronomy. Astronomers have watched bright patches drift steadily through the molecular gas at what appears to be the speed of light, illuminating one region and then the next. Nothing physical travels along with it, for only the news of the flare is moving. What is moving is not matter but a wavefront of illumination, the leading edge of an old flash sweeping outward. You can quite literally watch light travel, spreading slowly across a cloud year by patient year. The 148th fact is that nobody knows exactly what Sagittarius A-star ate 2 centuries ago to produce that flare. The favored possibilities are modest ones: a clump of gas torn from a nearby cloud, or perhaps an unlucky asteroid or planet that wandered too close and was pulled apart. It would not have taken very much. A black hole that ordinarily consumes almost nothing can brighten dramatically on a single decent mouthful. Somewhere out there, some small object met its end, and its brief obituary is still arriving in our telescopes. The 149th fact is that in the year 2010, astronomers analyzing data from the Fermi Gamma-ray Space Telescope found something no one had anticipated: 2 enormous bubbles of glowing gas rising above and below the center of our galaxy. They had been hiding in plain sight, spread so broadly across the sky that they were mistaken for background. The bubbles are so large and so diffuse that for years they had simply been subtracted away as background. Once recognized, they were unmistakable. Our galaxy, it turned out, has been wearing a colossal pair of luminous lobes for millions of years, and nobody had noticed until then. The 150th fact is that the Fermi bubbles reach about 25,000 light-years above the galactic disk, and the same distance below it, for a total span of some 50,000 light-years. That is half the width of the entire Milky Way. Their outer surfaces are surprisingly sharp, which suggests a shock front rather than any slow leaking. If our eyes could see gamma rays, these two vast bubbles would fill a great portion of the sky, arching enormously above and below the band of the Milky Way. They are among the largest single structures in our galaxy, and they are centered precisely on Sagittarius A-star. The 151st fact is that the energy stored in the Fermi bubbles is staggering, equivalent to something like 100,000 supernova explosions. Whatever created them released more energy than our sun will produce in its entire lifetime, many times over, and blew it outward in two opposing directions perpendicular to the galactic disk. The energy involved is comparable to everything the whole galaxy radiates in 100,000 years. The gas within them is thin and extremely hot, glowing faintly in gamma rays where fast particles collide. They are the fossil remains of an event that must have been, for a while, magnificent and terrifying to be near. The 152nd fact is that in 2020, an X-ray telescope called eROSITA found something even larger, a pair of bubbles enclosing the Fermi ones and reaching considerably farther still. The eROSITA bubbles span some 45,000 light-years above and below the plane, glowing in soft X-rays where the expanding shock front heats the surrounding gas. They confirmed that whatever happened at the galactic center was not a modest local event, but something that reshaped an enormous region of our galaxy. The Milky Way, it seems, has had a violent past. The 153rd fact is that estimates of the age of these bubbles vary, but most place the event that made them somewhere between a few million and 20 million years ago. That is very recent in cosmic terms, long after the dinosaurs, well into the age of mammals. Dating them depends on the measured speed of the expanding gas and is necessarily somewhat approximate. Our distant primate ancestors were alive somewhere in Africa while the galactic center was blowing enormous lobes of hot plasma out into intergalactic space. They would have noticed nothing whatsoever, of course. But it was happening above them all the same. The 154th fact is that the most natural explanation for the bubbles is that Sagittarius A-star went through a period of vigorous feeding and became, briefly, an active galactic nucleus. A large infall of gas would have driven powerful outflows in jets, punching out through the thinner gas above and below the disk and inflating the great lobes we see. Nearly every galaxy appears to pass through such phases on and off across the whole of cosmic time. It need not have lasted long, perhaps only a few 100,000 years. Our sleepy black hole may simply be a former quasar, resting after a very long night. The 155th fact is that there is a competing explanation, which is that the bubbles were blown not by the black hole but by a great burst of star formation in the central region. Thousands of massive stars, forming together and dying in rapid succession, could drive a powerful wind outward. The central region has certainly formed a great many massive stars in the geologically recent past. The truth may well be some combination of both. Astronomers continue to argue the matter carefully, testing each idea against the shapes and temperatures observed. It is an open question still being worked out, which is a perfectly comfortable state for a question to be in. The 156th fact is that there is separate evidence, from an entirely different direction, for a major flare about 3.5 million years ago. A long stream of gas trailing the Magellanic Clouds, far below the galactic plane, shows signs of having been strongly ionized by a burst of radiation from the direction of the galactic center. Working backward from the light travel time gives an event within the last few million years. Two independent lines of evidence pointing at roughly the same era, which is how confidence is quietly built. The 157th fact is that 3.5 million years ago, our ancestors were already walking upright on the plains of eastern Africa. They were small and they used simple stone tools, and they looked up at a sky far brighter towards Sagittarius than ours. The creatures alive then were the ones from which our own kind would eventually descend. Whether any of that flare's light penetrated the dust to reach them, we cannot say. But it is a strange and moving thought that the last great awakening of our galaxy's heart happened within the span of the human family. A piece of family history written in gas. The 158th fact is that over the whole 13 billion years of the Milky Way's life, Sagittarius A-star must have grown from something very much smaller into the 4 million solar masses it holds today. Each meal added a little. Its growth was probably concentrated into a few brief episodes rather than spread smoothly across the ages. Each merger with a smaller galaxy may have brought another black hole to join with it. The quiet trickle we see now is the last, faint continuation of a process that has been going on since the universe was young. Everything it has ever eaten is still there, inside, and it will never give any of it back. The 159th fact is that how supermassive black holes first came to exist remains one of the genuinely great unanswered questions in astronomy. Some suggest they began as ordinary stellar black holes and grew steadily. The earliest black holes we can see were already enormous when the universe was still very young. Others argue that the earliest ones formed directly from enormous clouds of gas collapsing without ever becoming stars at all. The discovery of very massive black holes in the earliest galaxies has made the puzzle sharper, for there hardly seems to have been time. Our own black hole's birth is a mystery, older than the Earth by far. The 160th fact is that when you consider the whole long history of it, the fierce youth, the great outbursts, the enormous bubbles, and then the long quiet that followed, there is something deeply peaceful in where the story has arrived. The storms are over. The heart of our galaxy has settled into a long stillness, and it has held that stillness through the entire span of human existence. We live in the calm afterward. Let that be a comfort as you drift now. Everything violent, long finished, and only the quiet remaining. The 161st fact is that the most important thing to know about Sagittarius A-star, as you lie here safely in the dark, is that it cannot harm you in any way at all. We are 26,000 light-years from it, which is a distance so great that light itself, the fastest thing there is, needs 260 centuries to cross it. No object at that distance has ever measurably affected anything whatsoever on this planet. Every fear anyone has ever attached to black holes evaporates completely at that range. It is not approaching. It is not reaching for us. It is simply, quietly, very far away. The 162nd fact is that gravity weakens with the square of distance, which means it fades astonishingly quickly as you move away from anything. Double your distance and the pull drops to a quarter. This inverse square law governs light and gravity alike, and it is a wonderfully forgiving arrangement. Multiply the distance by 10 and it drops to 100th. Across 26,000 light-years, the pull of even 4 million suns dwindles to something so faint it can barely be spoken of. Gravity is by far the weakest of nature's forces, and it is only ever noticeable because mass piles up. Spread thin across such a gulf, it is nothing. The 163rd fact is that the gravitational pull Sagittarius A-star exerts upon you, right now, is precisely the same as the pull of any 4 million solar masses at that same distance. A black hole has no special reaching power, no extra attraction, no hunger. Physics knows of no special attraction belonging to darkness, or to holes, or to anything frightening. Its gravity is entirely ordinary and follows exactly the same law as the gravity of a stone or a planet or a star. If you replaced it with 4 million ordinary suns spread over the same small volume, nothing whatever about its pull on us would change. Not by the smallest measurable amount. The 164th fact is that even in holding our solar system in its long orbit, Sagittarius A-star plays almost no part at all. The mass that keeps us circling is the combined mass of everything inside our orbit, roughly 100 billion solar masses of stars, gas, and dark matter spread through the inner galaxy. The black hole contributes about 4 million of that, which is 1 part in 25,000. Remove it entirely and our orbit would scarcely notice. It does not rule the galaxy. It simply sits at the middle of it. The 165th fact is that the most persistent myth about black holes is that they suck things in, and it is worth setting down plainly that they do not. A black hole does not vacuum, does not pull harder than its mass allows, and does not draw distant objects toward itself. The word suck has no place at all in any careful description of how gravity behaves. It attracts exactly as any other object of the same mass would. Things fall into black holes only if they happen to be aimed almost directly at them, which in the vastness of space is extraordinarily rare. Most matter simply orbits, forever, and never falls at all. The 166th fact is that the clearest way to see this is a small thought experiment beloved of astronomers. If our sun were somehow replaced this instant by a black hole of exactly the same mass, the Earth would continue in precisely the same orbit at precisely the same speed, forever. The same would be true of any star anywhere that might quietly collapse tomorrow afternoon. Nothing about our path would change in the slightest. We would freeze, of course, for there would be no light, but we would not fall in. Gravity does not care what shape the mass takes, only how much of it there is. The 167th fact is that Sagittarius A-star is not moving toward us in any meaningful sense, and never will be. It sits essentially still at the center of the galaxy while we circle it in a wide, stable, comfortable orbit that has held for 4.5 billion years and shows no sign of changing. The rotation of the galaxy carries us around the center, and never toward it. Our orbit is not a slow spiral inward. It is a closed path, no more likely to decay than the Earth's path around the Sun. We are not falling toward the center. We are simply going around it. The 168th fact is that for anything to fall into a black hole, it must first lose almost all of its orbital motion, and there is no easy way to do that. An object in a stable orbit carries angular momentum, and that momentum must be shed before it can spiral in. In the near vacuum of space, there is essentially nothing to shed it against. This is why the black hole feeds so poorly, and it is also why we are safe. The universe is very bad at delivering matter to black holes, which is a fortunate design. The 169th fact is that even the brightest flares of Sagittarius A-star pass over us without the faintest consequence. A flare that brightens it 100-fold still leaves it dimmer than a single bright star, and by the time that light has spread across 26,000 light-years, it is diluted beyond measure. Its very brightest recorded moments remain many millions of times fainter than the sun appears to us here. Add to that the thick curtain of dust between us, which absorbs almost everything in visible light. We are shielded by distance and then shielded again by dust. Nothing arriving from that direction has ever troubled the Earth. The 170th fact is that the scale of our separation is worth pausing over The event horizon of Sagittarius A-star is about 24 million kilometers across. Distances within the galaxy are so enormous that almost nothing ever influences anything else at all. Our distance from it is about 246 quadrillion kilometers. The ratio is something like 10 billion to 1. If the black hole were shrunk to the size of a small coin, we would be sitting well over 1,000 kilometers away from it. Nothing that small, that far off, can reach across such a gulf, no matter how heavy it happens to be. The 171st fact is that our solar system's orbit around the galactic center is remarkably stable and unhurried, sweeping through the quiet outer disk at a steady 230 kilometers each second. It rises and falls gently through the plane of the galaxy every few tens of millions of years, like a horse on a very slow carousel, and it drifts a little in and out. That gentle rising and falling is sometimes called the vertical oscillation of the solar system. But nothing about it trends inward. In 4.5 billion years we have not measurably approached the center. And in the next 4.5 we will not either. The 172nd fact is that Sagittarius A-star does emit gravitational waves whenever something falls into it, but these two are utterly harmless. A gravitational wave stretches and squeezes space itself as it passes, but by fantastically tiny amounts, less than the width of a proton across the width of the Earth. Our most sensitive instruments strain to detect them at all. They pass through you constantly, from mergers all across the universe, and you feel absolutely nothing. Space ripples gently, and the world does not notice. The 173rd fact is that astronomers speak of a black hole sphere of influence, the region within which its gravity dominates over everything else around it. For Sagittarius A-star, that sphere extends only about 10 light-years. A small bubble in a galaxy 100,000 light-years wide. Outside that small bubble, the black hole is simply one more mass among 100 billion others. Inside it, stars orbit the black hole. Outside it, stars orbit the general mass of the galaxy and hardly know the black hole exists. We are more than 2,000 times farther out than that boundary, comfortably, permanently, outside its little kingdom. The 174th fact is that even in the far more energetic past, when the galactic center flared and blew its great bubbles, the Earth came through untouched. Life on our planet has continued unbroken through every one of those episodes, through the outburst that made the Fermi bubbles and through whatever happened 3.5 million years ago. The oldest fossils of complex life on Earth are older than the making of the Fermi bubbles. The fossil record shows no galactic catastrophe. Whatever the heart of the Milky Way has done in the past, our distant corner has simply gone on turning green and wet and undisturbed. The 175th fact is that if Sagittarius A-star were somehow to awaken fully and blaze as a quasar, we would notice it mostly as a matter of curiosity rather than danger. From 26,000 light-years, and behind all that dust, it would appear as a bright point in the southern sky, perhaps rivaling the brightest stars. The intervening dust would soften and redden whatever small amount of that light did reach us. Astronomers would be delighted. The rest of the world would carry on much as before. Distance is an extraordinarily effective form of protection, and we have a great deal of it. The 176th fact is that the Sun itself will grow old and swallow the inner planets long before anything of galactic consequence happens to us. In about 5 billion years our star will swell into a red giant and end its ordinary life, and in all that time the Milky Way will have turned only about 20 more times upon its axis. The threats to Earth, such as they are, come from close to home, not from the galactic center. The black hole will still be there, quietly turning, long after our sun has gone quiet. The 177th fact is that Sagittarius A-star does not know we exist, and this indifference is perhaps its greatest kindness. It has no awareness, no intention, no direction of attention. There is simply nothing there capable of having a preference about anything at all. It is not watching, not waiting, not hunting. It is a region of curved space, obeying three simple numbers, doing exactly what mass and geometry require and nothing more. There is nothing to negotiate with and nothing to fear from. The heart of our galaxy is simply a fact, impersonal, patient, and entirely uninterested in us. The 178th fact is that, in a very real sense, we owe the black hole our stability rather than any danger. The presence of a settled, quiet nucleus is part of what makes the Milky Way a calm, unremarkable, life-friendly galaxy. Astronomers sometimes describe the Milky Way as unusually well-behaved for a galaxy of its size. Galaxies with raging active nuclei bathe their inner regions in hard radiation. Ours does not. The long quiet of Sagittarius A-star is one of the many quiet conditions that allowed complex life the billions of undisturbed years it needed. A sleeping heart and a peaceful house because of it. The 179th fact is that when astronomers speak of black holes now, the tone has changed a great deal from the anxious language of 50 years ago. They are no longer thought of as cosmic drains or devourers, but as ordinary, common, remarkably simple objects, present in nearly every galaxy, quietly doing very little most of the time. Understanding a thing properly is very often the quickest way to stop being afraid of it. Familiarity has replaced dread. The more closely we have looked at Sagittarius A-star, the gentler it has turned out to be, a neighbor rather than a threat. The 180th fact is that you may lie here tonight in complete safety, knowing that the dark heart of our galaxy is turning quietly 26,000 light-years away and will do exactly nothing to you or to anyone. It did nothing yesterday. It will do nothing tomorrow. It has done nothing to us through every generation of every family that has ever lived. There is no need to guard against it, no need to think of it with anything but wonder. Let go of any last small worry about it now, and simply rest. The 181st fact is that the great Andromeda galaxy is drifting toward us through the dark at something like 110 kilometers each second, and in about 4.5 billion years the two galaxies will meet. It is the only large galaxy anywhere that is approaching rather than receding, drawn by the mutual gravity of our small local group. The two galaxies are already close enough that their vast outer halos may be gently touching. When it arrives, the Milky Way and Andromeda will pass through one another, draw apart, and fall together again, over a span of hundreds of millions of years. A slow, graceful, unimaginably enormous embrace. The 182nd fact is that when the two galaxies finally settle, they will have become one, a single great elliptical galaxy that astronomers have already playfully named Milkomeda. The graceful spiral arms will be gone, scattered and rearranged into a smooth, rounded swarm of aging stars. Great elliptical galaxies are what most large mergers between spirals eventually produce. From whatever worlds exist then, the night sky would look nothing like ours. There would be no band of Milky Way across the heavens, only a soft general glow in every direction. The two galaxies of our childhood blended quietly into one. The 183rd fact is that when galaxies collide, almost no stars ever actually strike one another, which is one of the most comforting facts in astronomy. Stars are so tiny compared to the distances between them that two galaxies can pass entirely through each other with essentially no direct collisions at all. The gas clouds, being enormously larger than stars, do collide, and that is where the new light comes from. It is more like two swarms of gnats crossing paths, or two clouds of smoke merging, then like a crash. Orbits are rearranged. Gas clouds slam together and blaze with new stars. But the stars themselves simply drift past one another, untouched. The 184th fact is that in the long aftermath of that merger, the two central black holes will begin to find each other. Andromeda's black hole is considerably heavier than ours, holding perhaps 100 million solar masses or more. As the merged galaxy settles, both will sink slowly toward the common center through a process called dynamical friction. Dragged inward by the gravitational wake, they leave among the surrounding stars. Over hundreds of millions of years, they will spiral gently together, two dark hearts, drawn quietly toward one another. The 185th fact is that once they come close enough, the two black holes will form a bound pair, orbiting each other in an ever-tightening dance. At first, the orbit shrinks by flinging away passing stars, one at a time, each encounter stealing a little energy. Astronomers call the difficult middle stretch of that journey the final parsec problem. Later, when they are close enough, the pair begins to radiate gravitational waves, ripples in the fabric of space itself, and those waves carry energy away steadily. The orbit shrinks faster and faster. The two grow closer and closer and closer still. The 186th fact is that at the very end they will merge, and for a few brief moments that single event will radiate more power in gravitational waves than all the stars in the observable universe combined shine in light. The whole of space-time will ring like a struck bell, waves spreading outward across the cosmos at the speed of light. Detectors sensitive to that range of frequencies are already being designed for flight in space. No one will see a flash. There will be no explosion, no sound, no fire. Only space itself shivering and then settling into stillness once more. The 187th fact is that what remains afterward will be a single black hole of perhaps 100 million solar masses or more, sitting at the heart of the merged galaxy. Its event horizon will be many times wider than the one we photographed, wide enough to swallow our whole solar system out past the orbit of Neptune. By then our own sun will long since have swollen into a red giant and grown cold and quiet. Sagittarius A-star will not have been destroyed. It will simply have become part of something larger, its 4 million suns folded into a greater darkness. Its long separate existence quietly ended. The 188th fact is that the merger will very likely wake our sleeping black hole up, at least for a while. Galaxy collisions drive enormous quantities of gas inward toward the center, and a well-fed black hole blazes. For some tens of millions of years, the heart of Milkomeda may shine as a quasar, brilliant enough to be seen across the visible universe. And then, as the gas runs out, it will fade again and settle and grow quiet, as ours has done, and as they always eventually do. The 189th fact is that black holes are, in the very long run, the most durable things the universe contains. Stars burn out in millions or billions of years. Nothing else in all of nature is quite so completely immune to the passage of time. Planets are ground away or swallowed. Galaxies disperse. But a black hole simply persists, doing nothing, requiring nothing, changing not at all. Long after the last star has faded and the cosmos has grown cold and dark, the black holes will still be there, turning slowly in an empty sky. They are the universe's most patient inhabitants, and the last ones to leave. The 190th fact is that even black holes are not quite eternal, for in 1974 Stephen Hawking showed that they must very slowly evaporate. Near the horizon, the restless quantum fields of empty space are disturbed in such a way that a faint whisper of particles leaks outward, carrying energy away. Hawking radiation has never been directly observed, and yet almost no physicist seriously doubts it. The black hole therefore loses mass unimaginably slowly, glowing with a temperature so low it is barely meaningful to speak of. It was one of the most surprising results in the history of physics that the darkest things in the universe are very faintly warm. The 191st fact is that the evaporation of Sagittarius A-star would take something like 10 to the power of 87 years, a number with 87 zeros after it. The present age of the universe, some 14 billion years, is not even a rounding error against such a span. A single grain of dust falling in would set that unimaginable clock back enormously far. In fact, the black hole is currently gaining more mass from the faint cold light of space around it than it loses to evaporation, and will keep gaining for a very long while yet. It cannot even begin to fade until the universe itself has grown far colder. The 192nd fact is that if the universe continues as it seems to be doing, there will come an era unthinkably far ahead, when black holes are essentially all that is left. The stars will have died. The galaxies will have dispersed into cold, dark, drifting remnants. And through that immense emptiness, the black holes will remain, slowly and silently evaporating over spans of time that make the present age of the cosmos look like an eye blink. The universe's long story ends in patience, and in quiet, and in dark. The 193rd fact is that there is something unexpectedly restful in thinking on such enormous stretches of time. Against 10 to the power of 87 years, every worry that has ever crossed your mind grows very small and very soft. The stars are quite indifferent to us, and there is a real and gentle mercy in that. Nothing you have left undone today will matter to the black hole at the center of the galaxy, and nothing you must do tomorrow will trouble it either. The cosmos operates on a scale so vast that it forgives everything by simply not noticing, and there is a great deal of peace in that. The 194th fact is that the light we photographed from around Sagittarius A-star left there 26,000 years ago, when the world was covered in ice and our ancestors were painting animals on cave walls by firelight. In all the ages between, that light simply traveled, quietly, through the dark, across an unimaginable gulf, until it fell at last upon a handful of dishes on a turning planet. Those painted cave walls and that traveling light began their journeys at very nearly the same moment. Everything we know of the galaxy's heart arrived that patiently. Nothing was hurried. Nothing could be hurried, and it came, in the end, all the same. The 195th fact is that we have wandered a very long way together tonight, from the teapot low in the summer sky to the crowded heart of the galaxy, from a hiss of static in a New Jersey field to a soft orange ring photographed by the whole turning Earth, and through all of it runs one quiet thread, a single dark point, turning patiently at the center of everything, asking nothing and disturbing nothing. Every single piece of it was found by someone patient enough to keep looking a little longer. There has been no danger in any of it, only wonder. And wonder is the gentlest companion into sleep. The 196th fact is that everything you have ever known, every person and place and hour of your life, has taken place upon one small world that has been quietly circling that dark heart the entire time, through every day and every night, through every joy and every difficulty. The Earth has been sweeping steadily along its long galactic orbit, carrying you with it at 230 kilometers each second. You have been traveling all your life and never felt a thing, held gently and moved gently and perfectly safe throughout. The 197th fact is that perhaps the deepest gift of Sagittarius A-star is the way it invites us to let go of our own scale for a moment, and to rest inside something far larger and far calmer than ourselves. The galaxy does not hurry. Slowness on such a scale is not emptiness at all, but a kind of deep and settled calm. It has never hurried. It simply turns, once every 230 million years, patient beyond any possible impatience. To lay one's mind against that slowness is to feel the day's small urgencies quietly dissolve, and to be reminded that you, too, are allowed to be still. The 198th fact is that there is nothing at all being asked of you now. Nothing to solve, nothing to carry, nowhere you need to be. The heart of the galaxy will keep turning whether you are awake or asleep, and it will turn just as faithfully through every hour of your rest. The night will hold you exactly as the galaxy holds its stars, without any effort whatsoever. Let your shoulders soften. Let your jaw unclench. Let the weight of the day settle away from you and sink quietly into the dark beneath you. There is only breathing left to do now, and even that will look after itself. The 199th fact is that as your thoughts grow soft and dim, you might imagine yourself drifting gently outward, up past the roof and the clouds and the cold, clear air, out past the quiet planets, and away along the great slow curve of the Milky Way toward its glowing center. There is no hurry out there, no fear, no weight of any kind, only the soft blur of countless suns and, far ahead, one small ring of warm light turning in the dark. The distance would take no time at all in a mind already halfway toward dreaming. Let yourself drift toward it now, easily and without effort, carried on the patient turning of the galaxy. The 200th fact is that long after this night has passed, and long after all our nights have passed, Sagittarius A-star will still be turning quietly at the heart of the Milky Way, holding its 4 million suns in perfect silence, keeping its slow and patient watch over a sleeping world, just as it does above you now. So let your thoughts grow quiet, and let the last of the day dissolve into the dark, and drift gently inward with that ancient turning heart, into the calm and endless night. Rest now, sleep well, and thank you for drifting with me beyond the stars.